Alright guys, Mr. Antonucci here, and in this video we're going to talk about infinite limits and vertical asymptotes, and in the next one we'll talk about limits at infinity as well as horizontal asymptotes. So for the most part we've looked at limits where x approaches a finite number and where the limiting value is also a finite number. Here we're going to look at two different situations, one in which the limiting value increases or decreases without bound, that's called an infinite limit, or where x approaches positive or negative infinity, and that's referred to as a limit at infinity. So we'll tackle infinite limits first, and it's important to remember that infinity is not a number. The infinity symbol, whether it's positive infinity or negative infinity, represents unboundedness in the positive or negative direction. What we want to do is investigate some limits graphically and numerically to get a better picture of what's going on here. Here's the graph of f of x equals 1 over x squared, and we want to investigate the limit as x approaches 0. Graphically, as x approaches 0, it looks as though the y values increase without bound, whether you approach 0 from the left or right. We can confirm this numerically by using a table of values. So if we start in the negative side and approach 0 from the left, and you can see that as I make the x values smaller and smaller, the y values get larger and larger. And this makes sense. 1 divided by a smaller and smaller negative number squared is going to result in a larger and larger positive number. Now, if I let x approach 0 from the right, same thing's happening here. As we approach 0 from the right, you will get a larger and larger answer. And we say that this limit is equal to infinity. For the next one, we'll look at x approaching 0 from the left of 1 over x. So here's the graph of 1 over x. As we approach 0 from the left, it looks like the graph decreases without bound. We can verify that using a table of values, and you can see that the y values are getting larger, but in the negative direction. And there we go. So we would say that the limit is negative infinity. And then similarly, you could see in the graph that as x approaches 0 from the right, the y values would approach positive infinity. This results in 4 possibilities for one-sided limits. You could approach the c value from the left and have a positive infinite limit or a negative infinite limit. And similarly, you could approach c from the right, and same thing, you could have a positive infinite limit or a negative one. And these 4 graphs illustrate each situation. So we'll investigate the limit of natural log x as x approaches 0 from the right. Now, remember, the domain of natural log x is x such that x is positive, so it's greater than 0. The graph of natural log, if we look at it, becomes unbounded in the negative direction as x approaches 0 from the right. And so we would say that the limit is equal to negative infinity. We switch gears and think about trigonometric functions. Several of the trig functions do contain infinite limits, particularly tangent, secant, cosecant, and cotangent. They actually have an infinite number of infinite limits because of the periodic nature of them. So another important understanding is when you have a situation where there's a limit of a quotient that results in a non-zero number in the numerator and 0 in the denominator. Sometimes I'll write it like this, number over 0. This is going to result in an infinite limit. So if both numerator and denominator are 0, then this is called indeterminate form. And we'll discuss those situations later in more detail. Let's go ahead and look at a couple examples here where this is the case, because the limit as x approaches 3 from the right of 2x plus 1 over x minus 3, you cannot use direct substitution because that would result in 0 in the denominator. So we can think about this. As x approaches 3 from the right, the numerator is going to approach 7, because that's just a polynomial, and the denominator is going to approach 0. But you have to be careful here. You're approaching 3 from values larger than 3. So when you subtract 3, you're still going to get a positive value in the denominator. So a number that's approaching 7 divided by a number that's getting closer and closer to 0 but still positive is going to approach infinity. Now this 7 over 0 with the plus there is not proper math notation. I was just kind of keeping track of our thought process there. Here we have the graph of the function as well as a table of values for x approaching 3 from the right. I zoomed out on the graph so that you could see the unbounded behavior more clearly, and you can see that as x approaches 3 from the right, the y values begin to increase without bound. For this second example, as we let x approach 1 from the left, we can't use direct substitution here either because a natural log of 1 is 0, so we know that the denominator is approaching 0. The numerator, as x approaches 1 from the left, is going to approach 1. The denominator, as x approaches 1 from the left, is going to approach 0, but it's going to approach it from negative values because natural log of a number between 0 and 1 is going to be negative, and the closer you get to 1, the closer that value gets to 0, but it's still a little bit negative. So if we have a number approaching 1 divided by a smaller and smaller negative number, then that is going to approach negative infinity. Again, this notation I used here, the 1 over 0 to the negative, was just kind of keeping track of our thought process. It's not actual math notation. So here we have the graph of x squared over natural log x, and we can see as x approaches 1 from the left, the y values decrease without bound. And that is also verified in the table, that as we get closer to 1 from values a little bit smaller than 1, the y values decrease without bound. Now we have 4 results when finding limits of the form number over 0 where the numerator is not 0. Now this is just a lot of kind of complicated notation that is just saying the limit from the left can either be positive or negative infinity depending on if the numerator approaches a positive or negative number and if the denominator is approaching 0 from a number to the left or to the right of 0. And all of these are in terms of left-handed limits, but the same can be said for one-sided limits from the right. Now we want to talk about vertical asymptotes. Here we have several illustrations of what can happen when a function has a non-zero numerator and a 0 in the denominator. In each case, these are said to have a vertical asymptote at x equals c. I circled that because x equals c is an equation of the line for the vertical asymptote, and that's illustrated there with a dashed green line. Now the definition of a vertical asymptote is when any of the following infinite limits is true. You either have positive infinity or negative infinity as x approaches c from the right or left. In this example, we want to find the vertical asymptotes of the graph of f equals x over x minus 3 quantity squared. Now the domain of this function is x such that x is not equal to 3. Because x equaling 3 will produce 0 in the denominator, and you have that situation where you have a number over 0. We want to take the limit as x approaches 3 from the left of the function. This suggests it has a vertical asymptote at x equals 3. And if you take the limit as x approaches 3 from the left, the denominator is going to become a smaller and smaller negative number. Squared would be a positive number, and then the numerator is going to approach 3. So 3 divided by a smaller and smaller positive number is going to be positive infinity. And then we also want to look at the limit as x approaches 3 from the right, and the same thing's going to happen. You're going to approach 3 over a number approaching 0 from the right, which is also infinity. So we would say there's a vertical asymptote at x equals 3. One situation that sometimes comes up is a weird situation with a piecewise function, and we want to know, does the following function have a vertical asymptote? Well, we know that the function is undefined at x equals 2 because there is an open circle here and the graph looks like it increases without bound on the right side of 2. Now we don't have a function to actually plug values in, but what we can do is graphically estimate the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. So from the left, as x approaches 2, it looks like the graph is approaching 2. From the right, as x approaches 2, the graph approaches infinity. Because a one-sided limit produced an infinite limit, we have a vertical asymptote at x equals 2. I want to relate this back to the definitions we looked at a minute ago. We have the limit as x approached 2 being positive infinity, but it was approaching 2 from just the one side. So we do have a vertical asymptote there by the definition. And I bring this up because often students think that a function has a vertical asymptote only if both the left and right hand limits are infinite. However, if either of the one-sided limits are infinite, then there will be a vertical asymptote for the function. In fact, you can have a vertical asymptote that goes to positive infinity on one side and negative infinity on the other side of your c value. So guys, that's it for this video. Hope that was helpful. Reach out if you have any questions.